Well, our last module was on solutions, and this module is going to be on solutions that are in a state of equilibrium. By the time we get through not only module 6, but module 7 and 8, all of those chapters are on equilibria in different areas. So by the time we get finished, you will be an absolute genius and expert on equilibrium processes. Hopefully in the first part of the chapter, everything that you learned about equilibrium in your first year course came back to you. I went ahead and put the expression for equilibrium constants up here on the board so that we would have it to refer to as we're going through today's lesson. Basically, what you need to remember is that for this standard equation, you're going to take the concentrations of the products raised to their stoichiometric coefficients, multiplied together, divided by the concentrations of the reactants raised to their stoichiometric coefficients multiplied together, okay? These concentrations, since we're dealing with the solution, are going to be in moles per liter, molarity. In the last chapter, we dealt a lot with this equation, delta G equals delta H minus T delta S. And I'm not going to derive this for you, but this is the equation we're going to be using here, where we're going to be looking just at delta G, but how it's going to be related to this equilibrium constant for the reaction. Now, we've got a couple of extra little things in here. This degree sign, or what that looks like, means that it's under standard conditions. It doesn't really mean degrees, but it does mean standard conditions. And again, from your first year course, standard conditions just means that you have a temperature of 25 degrees Celsius and a pressure of 1 atmosphere, okay? Notice you've got a negative sign here. Don't forget that. That's really important. R is the ideal gas constant. And when we talked about gas laws in your first year course, we used a gas constant that had a number 0.0821. This one is different, but that's because the units on it are different. So this is the one that is going to work best in this equation so that we can get things canceled out appropriately. And then your temperature must always be in Kelvin. Recall, if you've forgotten, that in order to find Kelvin, you're going to take the Celsius temperature and add 273.15 to it to get the temperature in Kelvin. And then K is your equilibrium constant. Now, there is a difference between a log log and a natural log ln. I'm not going to go into that here if you don't remember that. I would suggest that you go back to your algebra book, check that out. But this is the equation that we're going to be using. And I can rearrange this equation to solve it for K. And so the way I would do that, I'll show you how this was rearranged. RT, LN, K. So if I divide both sides by a negative RT, then what that's going to give me is negative standard delta G over RT equals ln K. And remember that if I'm solving an equation, if I'm trying to isolate something, I have to do the opposite of what was done to it. So if I was going to, if I'm going to divide, then what had to be done? I'd multiply. We always do the opposite. Well, the opposite of taking a natural log is raising it to the power of E. So that gives me this. So I'm going to have K equals E to the power negative delta G standard divided by RT. Okay, now does that look messy? Yes, it does look messy, but it's not difficult to work with. And when we do an example here in a few minutes, I'll show you how to deal with that. The important thing to remember is what the effects of this is. And so I'm going to actually box those so that we can refer to them easily. If delta G is very big and very negative, okay, if you think about what happens if I put something in here that's, first of all, if it's negative, then it's going to be this negative times a negative delta G, which is going to turn positive, okay? And if delta G is large, that's going to make, it means you're going to take E and you're going to raise it to a big power. So you're going to multiply E by itself numerous times. that's going to make K very large also. If you have a very, very large number for K, what's going to be true? Well, if you have a large number for K, that means that the concentrations of your products are very, very big. And so if they're very large and I have very, very few reactants left, then basically my reaction is going to go to completion, okay? The author of your book said, and this is true, basically, in actuality, every reaction is an equilibrium reaction. You're never going to get a reaction that goes all the way to completion. A lot of them are going to be kind of balanced somewhere in between. Some of them don't work at all, it seems like. Okay, so this is how we're going to determine how far that equilibrium goes. Now, if delta G is small and negative, so if this is a small number, if it's negative, then the negative here is going to multiply by the negative delta G. Is going to still end up being a positive number up here. So E raised to a small number is going to be a relatively small equilibrium constant. And so if this number is relatively small, that means that these two are relatively in balance with each other. But if it's greater than 1, that means that my equilibrium is going to be weighted towards the products. On the other hand, if I look at a delta G being positive, if my delta G is positive, that means this whole number is negative. Well, what does a negative exponent mean? Well, that means that basically you're taking the reciprocal of it. You're putting it 1 over a number, which makes it very, very small. So if I have a small positive number up here, this is going to make this a fraction, which means it's going to be less than 1. And so if this number is less than 1, again, this is a fraction, so that means that my bottom is bigger than the top. So that means the equilibrium is going to be weighted towards the reactants in place of towards the products. Okay, so small positive delta G means that I have a small equilibrium constant. It's going to be less than 1. It's still positive, but it's going to be less than 1, and it's going to be weighted towards the reactants. Okay, now if I have a large positive delta G, think what happens here. I got it's a big number, but because it's negative, I have to flip it and put it in the denominator. When I put that in the denominator, that makes a very, very tiny fraction. And so that means that K is going to be very, very small. If this number is very small, then that means that my bottom number is big, my top number is small. So what's that mean? Well, that means that my reaction is so heavily weighted towards towards the reactants that it really doesn't happen at all. And for all practical purposes, I can say that it doesn't happen. Okay, so let's look at a couple of examples to see how this plays out. I'm not going to work all of the parts from example 6.2 because once you understand how to do the math for one of them, you're going to get it for all of them, and it's not difficult. So I'm going to work through part A and part C on this. All right, so the book says the delta G's for 4 reactions at 25 degrees Celsius are given below, and it says it's standard conditions. So in each case, we're supposed to determine what the equilibrium constant is and then state whether the reaction is equilibrium, whether it's a complete reaction or whether it doesn't occur at all. And if it's a complete reaction, is it weighted towards the reactants or towards the product? So we're going to base that question, that answer on how big our K actually comes out to be. So for part A, our delta G is a negative 1203 joules per mole. So this is example 6.2, part A, and delta G is negative 1203 joules per mole. Okay, now I want to have, I want to solve for K, so this is the equation that I'm going to use. So I'm going to use K equals E to the negative delta G over RT. Okay, that's the equation I'm going to use. So that I'm going to plug these numbers in. So K equals E to the negative 1203 joules per mole divided by R, which we said was 8.314 joules per mole Kelvin, times the temperature. And the temperature was 25 degrees Celsius, but if I add that to 273 to end up with a Kelvin temperature, that's going to give me 298.2. Okay, notice that I am keeping track of significant figures here. And so because they told me that the temperature was 25.0 degrees Celsius, when I add 273.15 to it, my last significant figure is going to be in the tenths place, so therefore I have 298.2 Kelvin. Okay. Tricky part here is basically just figuring out how your calculator works. So what you want to do is go up here to this exponent and get this part typed in first. So you're going to type in 1203. This negative and this negative are going to cancel each other out and make it positive. So you can just type in a positive 1203 divided by 8.314 divided by 298.2. Okay, when you do that, you should end up with K equals e to the 0.485 power. Okay, again, it's because I need three significant figures. Why do I need three? Because the original temperature that I used, the 25.0 degrees Celsius, that had three significant figures in it. So I'm putting three significant figures here, all right, because it's a multiplication and division problem. Yes, I realize that technically this has four, but that's where we're getting the three from, because the 25.0 degrees Celsius had three significant figures. So then once you have 0.485, what you need to do is figure out how to make your calculator take e to the 0.485. Usually you're going to type in 0.485, and then you're going to have to end up hitting the inverse of the natural log, which is ln. It's not log, it's ln. So play with your calculator and make sure that you're getting the correct numbers here. So then if I take that, you should end up with 1.62, okay? There are three significant figures to the right of the decimal point in this log, and so I should have three significant figures here, and this is a slightly different significant figure rule than we've used before. It actually is, he states it in bold print down on the bottom of page 165. He says, when raising a number to a power that has error in it, okay? This had error in it because the temperature was measured to three significant figures. So this, remember, E is just a number. It's an irrational number, 2.7 something, whatever the whole thing was. I'm raising a number to a power that has an error in it. The significant figures are determined solely by the number of significant figures to the right of the decimal. So three significant figures to the right here gives me the total number of significant figures over here, okay? The number of significant figures to the left of the decimal point is not relevant. So again, just another significant figure rule for you to be cognizant of. So I end up with an equilibrium constant of 1.62. Well, what does that mean? Well, if I look over here, 1.62 is certainly not very large, but it is greater than 1. So what that tells me is that my equilibrium is going to be weighted towards the products, okay? That probably should have been obvious because this number, is that small and negative? Well, that's kind of a judgment call on your part, which is why we went ahead and figured it out. But generally, when we think in terms over here, if we have a very large K, we're going to be talking, 10 to the, to a very large power, or a very small K is going to be 10 to a very negative power. It's not going to be something that's close to 1. So it's greater than 1, but it's not a whole lot greater than 1. It's not like 50 or 200 or 375 or something like that. It's a relatively small number, okay? Now let's look at part C, On part C, it says that our delta G is a negative 167 joules per mole, or kilojoules per mole rather. And that is kilojoules, so you need to be careful that you're watching your units on that. So since I already had all this written out, I'm going to kind of cheat here. And I'm going to go ahead and pop this in here. But because this is kilojoules, when I put it down here in this formula, it's got to be changed to joules. So this is going to be negative 1.67 times 10 to the 5th. Okay, so this is a much larger delta G than I had before. Okay, so get rid of this since we're going to be redoing that. So now when I type just the exponent pieces into the calculator, what am I going to end up with? Well, at this point, you're going to end up with e to the 67.4, okay? Again, 3 significant figures in the exponent. How many significant figures are there going to be in the answer? Significant figure rule tells us that I'm only looking at the digits to the right of the decimal point, so it's 1. I'm just going to have 1 significant figure in the answer, and if you take e to the 67.4 power, remember what that actually means. You're taking e times itself 67 times, okay? So when I solve that, that's going to give me 2 times 10 to the 29th. Okay, that's obviously a absolutely huge number. And so when I have a K that is that big, when it's very large, then that means essentially that reaction is going to go to completion. Okay, there's not going to be any reactants left. Okay, so when we talk about very small, very large, that's what we're talking about. We're talking about absolutely huge numbers. He worked out parts B and D for you. Again, I think you can probably handle those on your own. But if you do look at that, in part B, you ended up with a K of 0.618 when you went through all the calculations and calculated that out. Well, 0.618 is less than 1, but it's not classified as very small. So there, your reaction's weighted toward the reactants. And then if you flip the page over and you look at page 166 and you look at part D, there he ended up with a K equal to 6 times 10 to the minus 57th. Again, an absolutely tiny number. And so when you've got that number that's very, very small, that reaction basically isn't going to happen at all. So while the very large and the very small components, that's something that you're going to, after you work a few of these problems, check your answers, you'll see, okay, that's considered very large. That's not considered very large. You'll pick that up relatively quickly. Okay.